Hi and welcome to the second demo of the Julia Static Analyzer. In the previous demo I've showed you a bunch of things about the ecosystem of the Julia Static Analyzer. We just deepened into a couple of warnings about null pointer exceptions. In this demo, indeed, what I want to show you is more in details what kind of warnings are raised by basic checkers. So, as you know, when you launch the analysis, you have this wizard, you have basic and advanced checkers. Up to now, what I told you is that basic checkers are aimed at cover at different range of quality, security, efficiency and style issues. Now I will deepen into the warnings, and in particular I will deepen into the warnings obtained on the OWASP WebGoat application. During the demo I will also compare a bit the results that Julia obtained with respect to what you get with FindBugs. The new name of FindBugs is SpotBugs, so in my Eclipse workspace I have SpotBugs installed. And in particular, I already ran both the analysis of the Julia Static Analyzer, you have seen already in the previous demo how to run it, and also of SpotBugs. I've been using the default settings for SpotBugs. So, SpotBugs does not have an own result view. It uses the standard markers of Eclipse, and you can see here that in the OWASP WebGoat application raised 32 warnings on the application. If you remember, Julia raised about 1,500 warnings. Why? Well, essentially, as I will show you later, because Julia is covering much more different properties than SpotBugs. But let's start with what you have already seen. So, critical, bug, actual null warning, and let's take the first one. So as you remember, in this case, Julia raised the warning because the employee variable parameter might be null, and in the message it's written that it might be null because an explicit null value from line 87, here we are line 74, might be passed here. So what happened is that the getEmployeeProfile initialized at line 87 a local variable to null. Then we have a bunch of statements, so essentially it was inquiring the database to see if there was a user with that ID and initializing the employee with the correct values. But if there was no user in the database, rather than you get an SQL exception, AU exception, or whatever, this profile value returned profile local variable might have been null. So null value flowing here, that is what is reported by the warning, but also this is a critical bug because what Julia saw is that the employee parameter was dereferenced without checking the nullness later, so it's a real potential null pointer exception. For this warning, Julia needed really to use the call graph, so it's semantic analysis. So we can see here on the left side that there is only one marker on this line of code, that is just the one from Julia. FindBugs didn't find it, essentially because it applies more, let's say, syntactic local analysis. So it was not able to see these different method calls, one returning a null value and the other one taking the potentially null value and referencing it. But now let's grab a similar warning. So if I grab the first colon null warning, we are still talking about potential null pointer exception, and this one says, look, are you sure that the receiver of method to string is not null? There is an explicit null constant from line 61. So here we have person to string, and we can see that this person is initialized to null at line 61 as reported by our warning. Here we are doing some stuff. But if an exception is thrown in the first two lines of the try block, then this catch block would be reached when person is still null, and therefore here line 79 person might be effectively null. Here we can see that there is another warning by Julia about another property, but also the third one, the possible null pointer dereference of person. This came from SpotBugs. So SpotBugs or FindBugs was able to find out that this might have been a problem, exactly for the same reasons of Julia. Why in this case SpotBugs was able to find the problem and not in the previous case? Well, because the problem here is inside the same method. So you can see that the person is assigned to null inside this method. There is no interprocedural reasoning about this. So since SpotBugs does not have this very semantic, deep, comprehensive analysis, In this case, it finds the problem. In the previous one, where you needed to traverse different nodes of the call graph, it was not able to catch it. So you can expect that for the same reason, if we go to the other warning I showed in the previous demo, the one with get parameter values, so a method returning an array, but instead of an array, it was returning a null value. So in this case, Julia raised the warning, just said, look, you're returning an empty array that is later referenced from some other classes, that is catcher.java at line 104. And we can see that effectively this is what happened. But here you need a interprocedural semantic reasoning. So as we can expect here, FindBugs didn't produce any warning on this particular issue. So let's stay still on the critical bugs. During the demo, I will go one step by the other until the minor info style issues. But for now, let's start from the critical things. Because as you can imagine, we start with an analysis with 1,500 warnings, so quite a lot. And you would like, especially if you are during an evaluation phase, you have to present the analyzer, or also you run the analysis and you want to focus on the most important things that most probably will be real errors. Well, let's start from critical bugs. So we go down from 1,500 warnings to 27. So it's something that can be easily managed in a couple of hours of work, for instance. So here we have other types of warnings. The float comparison warning. So this is about floating point computation. So it's something that you might also have seen in C, C++, this kind of issue. But here what Julia spot out is that you have an unsafe comparison between non-integral numbers that might be approximated because of some previous computation inside this class. So in particular, what it sees is that you have a floating point value that is the result of some computation, and you have an inequality comparison over floating point values. So this is a critical bug because, since some computation was done before, well, the best would be just to compare if it's less than an epsilon and greater than an epsilon, not really equals to 0. And this is what is reported by the warning. This is a type of issue, for instance, that FindBugs does not find because it's not checking this type of properties. Then we have different warnings, of course, about null pointer exceptions, but I think I've been already quite deep on this type of issue, but also on more, let's say, object-oriented issues. What I mean by object-oriented issues? For instance, we have a warning saying method compared to seems inconsistent with method equals that is inherited from object. What this means? Well, first of all, we need to know what is a compared to method in a Java class. So this class implements the comparable interface. The comparable interface defines only one method, compare to, that has some constraints. In particular, if two objects are equals, then compare to has to return 0. Why this? Well, compare to is used by different libraries, in particular by different data structures. If this invariant, so if two objects that are equals do not return 0 when we invoke the compare to method on them, at that point we might have very strange subtle behaviors, also quite hard to debug. For instance, you might have a tree set in which the elements are not really ordered, or maybe the same element is contained twice rather than you remove an element and the element is still there. So this is a very, very important invariant you get. So Julia, so here is that you define method compare to that says, look, this two things are compared with respect to their name. So if the name of the two instances of this class is the same, then they are the same. We can see that, of course, there is also another value, but you might have two instances of this class with different references because there are two distinct instances, but with the same name. But since here, in this class, you are not redefining method equals, you get the one that is inherited from object. And this one does reference comparison. So Julia here correctly spot out that the compare to definition is not coherent with the equals definition. In this case, we can see here that FindBugs does not cover this type of issue. Another very similar issue is about equals and dash code. So in this case, we are defining the equals method, but we are not defining the hashcode method. What this means, the class object in Java says that you have the equals and the hashcode methods. If two instances of the class are equals, then their hashcode has to be the same. Why this? For the same reasons that compare2 should be 0 if two instances are equals. Otherwise, with data structures, with sets, hash maps, and so on, things can start to be very, very messed up. Okay, so same type of properties. This is kind of properties that I think also the Java compiler partially covers, but we can see here that is also covered by spotbugs. So the first marker here at this line is produced by spotbugs. So in this case, spotbugs was able to find this issue, and as you can imagine, it's not really an issue that is particularly hard to find. Running just the basic checker produces also some warnings about security. So in particular, between the basic checkers, we have the basic injection that is a very optimized and simplified version of the injection checker. So this checker is able to find very, very simple like SQL injections. The injection checker covers much more issues. So if you run the injection checkers, you get much more feedback and warnings than just with the basic injection checker. And here we might have an SQL exception because of how this query is built, about these parameters that are passed to the query. So injection is covered also by FindBugs. I think with the standard default settings you don't cover the security issues. In this case I didn't get a warning on these lines of code by spotbugs or FindBugs. Then about method calls. So in this case we have a method call, the replace all method call. So this is a method of the string class. What replace all does, we can go inside and see the documentation. Well, essentially it's a rather complex definition, but it says that replace all takes two parameters, okay? The regular expression that the string should be matched and the string that should be used to substitute for each match. And the returned value is the string in which these things have been replaced. So this is very important. We call replace all, but the receiver of the method call is not modified. The receiver, after the method call, won't have replaced all the regular expressions in the first parameter with the second parameter. The returned string will have this property. So here Julia spot out that we are calling a pure method. The replace all does not have any, let's say, side effect, but the returned value was not caught. So here it's a critical bug because this is definitely a sign that probably the developer completely misunderstood the API of the library. We can see here that there is also a warning by FindBugs saying that the return value was ignored. So also this property is covered by FindBugs, spotbugs. So I think this covers already all the different types of critical bugs we get. As you can see here, spotbugs did quite a good job. I think it covered more or less half of the issues that were also discovered by Julia. If you remember, we started 30 warnings by spotbugs, 1,500 by Julia. So in this case, spotbugs cover more or less half of the issues. So this is quite effective. That's a quite good result. But the point is that spotbugs is really focusing on these, let's say, critical issues. It doesn't provide a wide coverage of different quality, efficiency, or style issues. And now you will see with the warnings I'm going to show you from now on. So essentially, all the most part of the next warnings will not be covered by spotbugs. So let's go with major bugs. So still bugs, but Julia thought that probably they are not so relevant with respect to what you get at a critical level. So we have a warning say, look, you have a formal parameter screen, so it's an assignment to unread parameter warning, to the formal parameter screen that is written before having been read. So here, effectively, we have a parameter of the method screen. We have a Boolean condition say, look, if x is equal to null, then assign screen and initialize it to a non-null value. So here Julia got a hint, say, look, probably since you are assigning it before even checking it, there is something wrong going on inside this method. In particular, probably we would expect that this s variable might have been the screen. So if screen is equals to the null, then initialize it. We can see here that we have also another warning saying, look, here at this code line, variable s can only be null at this program point, because we see that s, if s is equal to null, then you call the constructor of error screen passing s, so passing null. Of course, this is let's say, I think it's a style issue. It's quite hidden later on in the different warnings you get from Julia. But here we got two warnings on the same lines of code, and definitely this is very, very suspicious. So another feature of the Julia analysis is that often at the same line of code you get many warnings. So I strongly invite you to start from the inspection, from saying, you know, the critical bug, major bugs, and so on, but always to give a look. If on that line of code you get more than one warning, maybe there are different types of issue because something got wrong by the code written by the developer. So here, definitely this should have been a screen equals to null and not an s equals to null condition at this line of code. Another issue that is about more object-oriented programming language is the dynamic cast of a variable. Here we have a warning by Julia saying, look, are you sure that the formal parameter request can be casted from a servlet request to an HTTP servlet request? Of course, no, you cannot be sure. You didn't check what's the dynamic type of the request. And if you don't get an HTTP servlet request, you get another servlet request, there you will get a class cast exception. So this is really about the dynamic casting of object instances inside Java. You can see here we have only one warning and one warning from Julia. Still, inside the major bugs, we have other warnings about security. Here we have a field or a local variable, no, I think it's a field password that is checked against a constant string, so it looks like you have a password hard-coded, rather than the use of an unsecure cookie. So you have a cookie that is added to a response without setting the security flag to true. That's another security issue. Or other than, you have a field that is logger. Inside the serializable class, you see you have also defined a serial version user ID, but this is not serializable. So, well, probably this should have been a static field, not let's say dynamic field. But if you serialize this object, definitely the serialization will get wrong. So still, this is more about object-oriented properties. We have also warnings about resources that are not closed at the end of a method. This is very important because in Java you have many different types of input-output streams, and it's extremely important, especially for files and this type of resources, also database resources, that you always make sure that the resource is closed at the end of the method, because if this is not the case, the resource will be open. So things that might happen is that the Java program retains the access to a file for a long while, or also doesn't free resources, memory resources, and so on and so forth. So here Julia reported that there is an instance of class statement that is created here, that it doesn't seem to be always closed at the end of the method, and then it gives some explanation why. And we can see here is that we have a try method in which we create the statement, we execute the update, but we don't close the statement. So if an exception is thrown, but even if the exception is not thrown. Similarly here we have a class input stream that is created. So we see the input stream we get from the context. Then it's added to the manifest. This is done other things, but it's not closed. So also in this case, this might be a problem. All these issues are not covered by FindBugs, so from now on, essentially, we won't find any of these issues covered by FindBugs. Then we have issues about results, so test whose result is fixed. So for instance, here we have that, okay, the message is quite verbose, that hints is always non-null. So you are comparing against a null, a new array list created at some program point, some other program points, and so on and so forth. So here you can see you get a warning here, and then a warning about bytecode just the line after. Of course, test is predetermined and reachable instruction warnings are quite related. If there is a test that is always true and false, and then there is a branch that is under the control of this Boolean condition, that branch might be dead code. So here definitely this hint is always not null, so this test is pretty useless, and this return statement will never be reached, so you can just remove this piece of code. Still about security in wiki hashing algorithm. So in this case, we have an instance of the MD5 algorithm that is nowadays outdated and should not be used anymore. We get a warning, so it's a major bug, but it's more about security issues. Okay. Then we go down up to minor warnings. So for instance, here we have a warning. It's a minor bug, and it says, look, do you write into a non-null array? It looks like there's an explicit null constant from line 248 flowing here. So at line 266, we have parameter types is the reference to assign its ith element. Here, line 248, we can see that parameter type is initialized to null. So Julia saw this as before. However, this is not a critical bug. This is a minor bug. Why? Because Julia saw many other things, in particular that this parameter type is initialized here when you get a condition over args token. If count token is greater or equal to 1, then parameter type is initialized to something that is not null. So here what else happens is that we have another condition always about args token, okay, that check if the args token variable has more tokens. So sure, if count tokens is greater or equals than 1, this will be true, but if this is 0, this will be always false, and therefore we cannot reach this line. So what happens? If we have at least one token, we initialize this variable, and if we have at least one token, then we access that variable. So this code is safe. Julia got a hint that maybe the analysis here might have lost some precision, because it was able to see two different conditions in the same local variable. But however, this is an environment that is definitely too complex for Julia to discover that if count tokens is greater or equals than 1, then this is always true and no other way around. So if it's 0, you will never enter this object. So it raised down the severity of the warning. Instead of producing a critical bug, it produced a minor bug, but still there was something suspicious. So this is definitely a false alarm. But as you can see, it's a minor. So you will find this type of errors, warnings, only after you have been taking care of like 300 warnings. So it's something that comes quite later. Other issues are about, let's say, dead code. So in this case, we have a field that is never read in reachable code. However, we can see that this local variable is read here. So Julia was wrong? Of course not. There is also a warning on this method saying, look, get default ranking is reachable. So this method is never called by any reachable public method. Therefore, this is dead code. And since this is the only method that accesses this local variable, we can see this is a private variable, and we just ask the Eclipse IDE who is reading it. It's just get default ranking. Then also the field is dead code. So here really it's a simple warning. We have a private field that is never read, but indeed the reasons why it's never read are quite complicated, and they needed the semantic model that is computed by Julia. Unused return value. We have a make dir, a call to a method that returns a boolean, and you didn't check if the directory was correctly created. Here, you remember, we had the replace all, so there was a method that was pure and whose return value was not checked. That was like a critical bug. Here's just a minor bug because this method make dir, of course, has side effects, not only in the memory, but has also side effects on the file system. So this is just, let's say, a minor bug issue. Or, okay, we have the uncalled warnings. So here, for instance, we have a method, parse employee profile, that is protected and it's unreachable, like the get default ranking method I just discussed in the previous warnings. Okay, so far so good. Then let's quickly explore also other categories of warnings, in particular about efficiency. So about efficiency, we have major efficiency problems. So some cases are about concurrency. So in this case, we have a blocking call, system.out.println, inside a synchronized statement. So I think we really need to read, because this method, you can see, is called by another class, database utilities, line 61. So let's open now database utilities at line 61, so it's just a few lines below here. Okay, we have a synchronized method that is then calling that method. So of course this might be increasing the probability, the monitor contention, as well also the probability that you might get stuck and get deadlocks. So this is an issue about efficiency, about concurrency. Fields that are only used in constructors. I have a field of a class, and this is just initializing the constructor, and it's not used by other reachable methods. So in this case, let's see what Eclipse says about this method. We can see that it's used in another, to initialize another field, but of course this is always inside the constructor, so it's only used inside the constructor. So what's the problem here? A field occupies memory. If you serialize, the class also occupies space on your hard disk, and so on and so forth. So it's an efficiency problem. You should avoid these kind of things, because might just, you know, consume more memory space in the disk than required. Same for field never used, or field should be replaced by local warnings. So for instance, we have this stage variable. So let's see from where it's referenced. Well, indeed it's referenced here. So here stage effectively is always initialized at the beginning of the method, and then it's read later. And there is no other method using this stage local variable. So what Julia says here is that, look, this field stage should be replaced by local variables. Therefore, it's not a field, should not occupy memory when you allocate the object. It might be just a local variable here inside this method, create content, and that's all. Just declare a stage variable here, and you will save memory when allocating this type of objects. Tautological instance offs, like here. So screen is initialized to a new error screen here, so it's always true, this Boolean condition, and you don't need to ask it again. Or, okay, useless calls, we have seen a bunch of them. Useless test, in this case you have a test, if something, and then you have a semicolon here. So, what happens here is that if this is true, then you do nothing. And then in any case, you execute a hints.add. So, definitely, okay, Julia thought that is a major efficiency problem. This is probably indeed a bug, so this semicolon character should not be here, because probably wanted to say, look, if get stage is different from 1, then add an int, otherwise don't add this type of int. However, you have a Boolean condition, you test the Boolean condition even with the method call, and then you do nothing. So this is definitely an efficiency issue as well. Minor efficiency warnings. Well, assigned to a unused variable warning. You have a variable that is assigned here, and it's never read later. We can see here that the same warning is raised by the Java compiler. All the warnings I'm presenting now, they are not covered by default by FindBugs. Or you have a field that is never used, or, okay, you have an efficient boxing of the class. So here you just say, you box, so you have a p-value here okay, that is a string. You box it to a boolean, and then you pass it as a native value boolean. So definitely this boxing of a boolean value that is immediately boxed afterwards is pretty useless. You should ask directly to parse it to a native bool, not to an object, an instance of the boolean value. Yet another efficiency issue. As you can see, as long as we go to less severe warnings, you get warnings that probably are not so interested for anybody. Maybe somebody might be also quite interested in these types of warnings, but they're definitely minor issues. This is the idea about the categorizations we have in Julia. Okay, here still we are going back to this to this field stage. We had a warning, just say you should replace it by local variables, but also that this value written here is never used. Why? Because this is in the constructor. You write one in the constructor. Then, as we have seen, there is only one method that uses it, and it always initializes it before reading. So definitely this is a useless field update. You can save this type of operations. Just remove the assignment. Finally, we have style issues. So style issues, still you can see we have about 800 issues about hard-coded file names. So in this case, you have an OS-dependent file name here that should be moved to some configuration files in order to be independent. But also we have quite a lot of use log instead of warnings. So there is this production checker. What the production checker does is to make a bunch of checks before putting the code into production. That's the idea. What it means? For instance, if you're using the console to print something, this is definitely bad. As soon as you put this code in production, nobody will be looking to the console. Okay, so you print something in the console and then it gets lost. What you should do, and this is also what is reported by the warning, is that you should replace the print line call with the logging method. So you should probably do some log.info trace rather warning. Okay, depends what type. So for instance, this probably should be a warning, while this should be just an info or a trace level logging. So about the minor issues, we have some issues like, if you remember, the returning null for an empty array. You return null instead of an empty array, but Julia didn't find any callee of the method that is dereferencing, because essentially the application that was under analysis didn't contain any call to this method, and the method was public, so was an entry point for the type of execution model we selected. And well, setting static in non-static warnings. So this is more about object-oriented features. We are inside the constructor and we initialize the static variable. You should initialize the static variable inside the static constructor, not the constructor of new instances of the class. Rather than generic exceptions, you have a catch block that catches generic exceptions. This is a bad style. It's like, I think, a minor style issue, so it's not very, very severe, but still, it's not good to catch a generic exception. You should catch, probably an SQL exception, an IO exception. Now I don't know exactly what kind of exception might have been thrown here, but just catching a generic exception in general is not a good practice. Even more, you might have empty exception handlers. So you catch an exception and then you do nothing. This is definitely a bad style practice. At least you should put some logging information, or you should try setting the state of the object or something like that. Because what will happen is that when you run this code, the exception is thrown, is caught, and nothing happens. So you don't trace that something bad happened in the middle here, and you don't know what's going on when something goes wrong. Rather than, okay, here you have a broad throws. So here you have a two-stage method that throws generic exception. You should be more precise. You should instead discover exactly what type of exception might be thrown here. So you can see you have a string buffer and so on. So I don't know exactly this. Probably this set stage is also throwing, let's see, a very broad. No, this is not throwing a very broad exception, but I don't really know even why in this case you see the developer wrote such conditions. But still, bad practice. You should not throw generic exception in the declaration of the method. The throws statement here should be quite more precise. I think that this ends the quite verbose, I hope not much boring overview of the different types of warnings raised by the Julia Static Analyzer. So as you have seen, FindBugs is able to find some things. As soon as you get reasoning about different program components, methods, or even heap accesses, at that point, SpotBugs, FindBugs is completely lost. It's not able to raise the same issues even if they are critical bugs. And then of course also the coverage when you use the standard settings of FindBugs, SpotBugs with respect to the ones of Julia. Well, at that point SpotBugs does not cover all our issues. So you have seen that as critical bugs are quite well covered, I would say 50% by SpotBugs, all the others are not. I hope you didn't get much bored about this very, very long presentation. I hope that at the end of this, you get a good feeling about what issues, what warnings are produced by basic analysis in Julia, and also how to deal to them, how to navigate, how to have an idea about what type of issue. And still, the last thing I want to tell you and remember you is that when you get a warning at a line of code, it's always good to look at other warnings at that lines of code if you run the basic checkers, because often you get different types of warnings on the same program components because there is one issue that raised many different potential errors by the analysis of Julia. So always have a comprehensive view of the analysis and of the warnings produced by the analysis on the piece of code you are analyzing and inspecting in that moment. Okay. Thank you very much for your attention, and let's see for the next demo.